Hello, my name is MD Mahbubuzzaman. So I'm going to present today the paper Optimally Blending Honeypots into Production Networks, Hardness and Algorithms. So mainly I'm going to talk about the honeypot deployment problem itself, the contributions that we have made so far, some experiments that we did, and limitations and future research. So as we all know that the defending cyberspace is an extremely challenging and complex task. And honeypot is a deception technique for luring and exposing cyber attacks. In traditional security system, the honeypot computers and the production computers, they stay in a different network. So when an attacker attacks, then through a router, it either goes to a production network or goes to a honeypot network. And if it attacks a production computer, then the production computer is compromised. And if it somehow doesn't able to manage, then it goes to the network of the honeypot computer, and the attacker strategy or tool is exposed. So sometimes it is easier for the attacker to predict like which network is for the production computer and which network is for the honeypot computer. So that's why the idea is to blend the production computer and the honeypot computers in the same network, so that it is confusing for the attacker to attack like which computer is the production computer and honeypot computer. He cannot separate. So, but there is a problem, like due to budget constraint, we can only deploy a subset of all honeypot computers. For example, here we see if we assume that the orange one is the honeypot computer, then we see the second one and the fourth one is deployed, but the last one is not deployed. So we call it a dummy computer. Okay, so let's see the honeypot deployment problem statement. So let's suppose we have n production computers and B is our budget. So and there is total number of n plus m IP addresses. So we index that from 1 to n plus m. So here we see that the production computers are in white circle and the honeypot computers are in the box. So we have at most m honeypot computers location in the IP address index from 1 to n plus m. But each time, for every time, like if the production computers are like fixed for a position, like when the IP address 1, this is production computer 1, I cannot make any decision for here. But when it is the third position, there is a honeypot computer. But in that honeypot computer, I have a decision to make. We can decide either to deploy a honeypot or not. And if we deploy the honeypot, then we incur some cost Bj. And if we decide not to deploy a honeypot, then we will call that IP address is empty, or we'll call that it is a dummy computer. So it doesn't incur any cost, but that position is fixed. Okay. So our optimizer will give us a priority of attack that is pi s, that is known in prior. So we know the attack sequence. And the attacker has a certain number of strategy or tool. Let's suppose it is the R equals to 2. So if the attacker has 2 tools, then it can, if a attacker attacks a honeypot, one of his tools will be exposed. And the attacker can keep attacking unless there is no tool left. So when a attacker attacks a honeypot, his tool is exposed. So when there is no tool left, he cannot attack. And the value of production computer J is Vj. Okay, so let's see an example so that it's easier for you to understand. Okay, now let's suppose there is an attacker who has 2 tools or strategy to attack, and the optimizer gives us the sequence. For example, this is the sequence. If we assume that the green one is the production computers and the orange one is the honeypot computers, and for simplicity, we haven't included any dummy computer here. We assume that all the honeypot computers is deployed, but there could be some computer like the orange honeypot computers that might not be deployed. The decision will be made by the algorithm. Okay, so let's suppose that the attacker has a probability of belief that whether a computer is honeypot or not. So for example, the first one, it has a probability that it believes it is a honeypot computer or not. So it takes a random number, or it's like it tosses a coin, and then it decides to attack the computer in the first IP address. So it attacks the computer, and Unfortunately, it was a production computer, so from the defender side, the loss will be V1. Okay, so the next time the attacker has now two tools, but it attacks the second one. So it decides for the second computer whether to attack or not. So it also has a probability of belief that whether this computer is honeypot or not. So let's suppose it takes from a biased coin toss, it decides to attack the computer. So it decides and then it attacks. And when it attacks, fortunately this time it is a honeypot computer. So since this is a honeypot computer, so the loss will not increase. So it will keep stay in V1, but one of the tool of the attacker will be exposed since this is a honeypot computer. So the attacker cannot use the same tool to attack a new computer. Okay, so next time, let's suppose the third computer, the attacker, the same way it toss a coin based on the prior knowledge he has about the computer, and he decides not to attack the computer. And it happens on the fourth computer too. So for the next time, it attacks the fifth number of computer. And unfortunately, it was again a production computer. So since this is a production computer, so the digital assets will be compromised. So that's why the loss will be V1 plus V5. The same way the attacker decides not to attack the subsequent one, then it attacks the seventh computer. The seventh computer was a honeypot computer. And since it attacked the honeypot computer, it will lose his last tool. So since the attacker doesn't have any other tool left, so the attacker cannot proceed to attack any other computers. So the total loss is now V1 plus V5. So this is how we can calculate the loss. And from a given sequence, we can calculate the loss of that sequence. And also we have a probability of occurrence of that sequence. And from that, cumulatively, we can get an expected loss. So our task is to minimize the expected loss. So yeah, so that's the problem statement. So if we give a standardized form, then the problem statement stands. Given an attack scenario, we have to choose a subset of honeypot computers within n locations to minimize the expected loss so that the total incurred cost does not exceed the budget B. In our first contribution, we successfully showed that the decision version of the HG problem is NP complete, and we deducted the NP completeness from subset product problem. Our next contribution is 1 plus epsilon Pitas algorithm, but before we move into the Pitas approximation algorithm, we want to show you the exact algorithm, how it works, because the Pitas algorithm would be a modified version of the exact algorithm. So the exact algorithm works in a dynamic programming fashion. So let's suppose we have some IP address location. So sequentially, the optimizer or the algorithm decides whether there is a honeypot computer or a production computer. So let's suppose the blue is for the production computer, and the next time it is a honeypot computer. So the algorithm decides whether we want to deploy that honeypot computer or not. So this like allocation of the computer is actually done in a sequential manner. So for that reason, we designed a record system. So it's like a table. So in the table, we have some information, like, for example, the first column information is the IP address. So the position of the computers is the IP address location. And the probability of R is the probability that what is the likelihood that R number of tool is exposed. So when the PR equals to 1, it means that the attacker has lost all of his tool. When the P0 is 1, it means that the attacker doesn't lose any of his tool. So it can continue attacking. And E is the expected loss and B is the incurred cost. So for example, initially, the attacker haven't started attacking, so everything is 0, but the P0, like there is no tool exposed. That's why the probability of P0 is 1. And the production in the IP address 1, we see there is a production computer. So this location is dedicated for that production computer. So we have nothing to decide here. So that's why this production, we say that in IP address 1, we only update the expected loss, because if that production computer is attacked, then it will be compromised. And that's why our expected loss will be changed from E to E prime. In the second IP address, we see that the optimizer has given there is a honeypot computer location. But we have two things to decide. either we can decide not to deploy. If we decide not to deploy the honeypot computer, so there will be no update, but it will be recorded in the table. But if we decide that to deploy the honeypot computer, so there are some things we need to update in the table. First of all, we need to update the probability values, because since there is a honeypot computer, so there is likelihood that computer will be attacked by the attacker, so that we lose some digital asset value. That's why, and if that honeypot computer is attacked, then the attacker might lose one of his tools. So that's why the probabilities are updated, and the expected loss will be the same as the previous one, because there will be no expected loss from the defender's perspective, since this is the honeypot computer. But to deploy a honeypot computer, we also have to update the incurred cost from B to B prime. And every IP address we move sequentially, we can eliminate some of the state. So if in two state, both of the state has the same expected loss, but we will keep the cheaper version and we will remove the costlier version. And this is how we populate until we reach to the n plus m IP address. When we reach to the last IP address, then we only keep the n plus m, like the last IP address, and we return the minimum of the expected loss from our record. And also we have to keep in mind that the total incurred cost cannot be greater than the budget B. Okay, so the 1 plus epsilon Peters algorithm is a modified version of the exact algorithm. So we actually use the same methodology, except we round the value of expected loss E, probability of I number of tool is exposed, PI and B to E cap, PI cap, B cap from a geometric gamma distribution. And since we have rounded that up, so that's why there is much possibility for elimination. And that's why this 1 plus epsilon approximation solution for the HC problem runs in n plus m over epsilon to the power order of r log b max time. Now let's talk about our experiment section. So we have studied that the optimizer will give us a attacking sequence, and we studied 3 types of attacker in order to generate the sequence. So we take the risk averse attacker, risk neutral attacker, and risk seeking attacker. So we take a exponential utility value uj that is parameterized by v sub j and alpha, where v sub j is the value of computer j and alpha is the coefficient of absolute risk version. And this alpha can range from -1 to 1. When it is 0, then it is risk neutral. When it is negative, then it is risk seeking. And when it is positive, then it's risk averse. And from that, we can rank the projects and get a sequence of attack. So in our first experiment, we try to see that what happens when different type of attacker attacks and what is the relationship with the relative loss. So we see that the most risk averse attackers have a very high variance of relative loss, and most risk seeking attacker has very low variance of relative loss. And from that, we find insight that risk seeking attacker is more predictable. In our second experiment, we wanted to see that what is the attacker's reconnaissance capability versus the expected loss to the defender. So in order to get the attacker's reconnaissance capability, we take the cosine similarity between a vector A and vector D. So this is basically is trying to say that how close the attacker is thinking like the defender, like in terms of value, in terms of probability that whether a computer is actually honeypot computer or not. So from that insight, we see that after 0.7 value of the cosine similarity, there is a peak. But before 0.7, it was very stable and the expected relative loss is very low. So we can say from that blending is extremely effective under a certain threshold value of attacker's reconnaissance capability. So in the limitation and future research part, we assume that the attacker's perception is not dynamic. So the attacker is have taken a decision, or it has a prior inference about the computers, and then when it attacks, whenever it got exposed or it successfully got a production computer in hand, it doesn't change its decision. So it's totally static. So in further research, we can see that whether it can be done in a dynamic way. we also assume that the attacker's capability is universal. We were thinking that, okay, the attacker has some tools or strategy. So not all of the strategy can work in the similar way for all computers. For example, if a environment runs with Linux, it sometimes some strategy is good for attacking a Linux computer, but not a Windows computer. And also we formalize the HD problem in a one-shot fashion. From the defender's perspective, it's also stable. Like we have made a decision and we don't change our decision in the phase of the attack. But if we can make it more dynamic, it would be good enough. So that's it. Thank you. If you have any question, you can ask.